All right, we are live on YouTube. Welcome everyone to the DevOps Online Summit. This is the DevOps Online Meetup. In this session, we have with us Arda Shah, is going to share with us principles, patterns, and practices for effective infrastructure as code. So Ardash, take it away.
Awesome. Thanks, Tom, for the introduction. I'm going to just start by making this full screen. Hello, everyone. Thanks for joining the session. As Tom mentioned, my name is Arda Shah. I'm a founder and CEO at Compuzest. You can find out more about us on our website. So today, I'm going to talk about principles, patterns, and practices for effective infrastructure as code. This session is based on my experience and my team's experience working with infrastructure as code over the years and helping various companies adopt best practices. So we have seen all kind of things from startups to enterprises and mid-level companies adopting infrastructure as code, and where the challenges they face, what are the principles and patterns and practices that have helped them. Right, so I'm sure you all know what IAC is. So I'm not going to spend too much time reading the definition, but basically what this says is that it's one of the key DevOps practices that enables teams to deliver infrastructure and the software running on it rapidly and reliably. First up, let's talk about the key principles that everyone using infrastructure as code should be aware of. And this might be too basic for some of the folks, but bear with me because I wanted to kind of cover those things quickly and then get into more details. The first one is idempotency. Idempotency helps in simplifying the provisioning of infrastructure and reduces the chances of inconsistent results. No matter how many times you run your IAC and what your starting state is, you will end up with the same end state. It can be achieved by using a stateful tool with a declarative language like Terraform, where you define the desired state, the desired end state of the infrastructure you want in code, and then it is Terraform's job to get you to that end state. If it can't get you to that desired state, it'll fail. So here, let's look at an example of what a non-idempotent and idempotent code looks like. So first off, let's say we want 3 virtual machines. We run our code. It gives us 3 virtual machines. Let's say we reapply the same code again. In case of non-idempotent code, it'll give us 3 machines again, unless we write some custom code to check if the machine exists. But that's code that we need to write, and we need to manage that logic. So in this case, you will end up with 6 actual virtual machines instead of 3. That is what we expected. In case of idempotent code, though, if you provision those same 3 VMs, you will get those 3 VMs for the first time. And if you reapply the same code, there won't be any change because it knows that those VMs already exist. So it's not going to make any changes. So you end up with 3 actual VMs, and that's what you expected. So in case of idempotent, a lot of things are taken care of. You define what you want, your end state, and it's infrastructure as code or whatever code you're using job to actually get you to that state. So configuration drift is a huge problem with infrastructure. It occurs when over a period, there are changes made to infrastructure that are not recorded, and your various infrastructure environments drift from each other in ways that are not easily reproducible. This usually happens if you have a mutable infrastructure that lives for a long time. The system is more brittle in general for long-lived infrastructure. Since issues like a slow memory leak, disk out of space due to long accumulation, etc., might occur over a period of time. It also means that you won't be provisioning the infrastructure as frequently as your application or configuration. And as a result, won't be confident in your ability to do so. So these issues can be resolved by using immutable infrastructure. Let's now look at an example of what a mutable and an immutable infrastructure looks like. So on the left side, again, let's say we want to provision our infrastructure, and we did that, our version 1 of our infrastructure, and the users are going to that, and then let's say you make some change to your code. You make a change, and then you apply the version 2 of your infrastructure. In case of mutable infrastructure, you would apply those changes to existing VMs in this case. So you will keep on patching, on applying changes to existing infrastructure. Again, what happens here is your infrastructure is long-lived because you are applying those changes to same infrastructure. In case of immutable infrastructure, though, once you have your version 1 of infrastructure and you make any change, you would just provision brand new infrastructure with version 2. Then what you would do is slowly route traffic, the live traffic for your users to this V2 version. And if everything looks good, you would get rid of the old version 1 infrastructure. In this case, any new changes would be applied to brand new infrastructure rather than keep applying changes to old infrastructure. So this way, we get rid of things, we don't have issues like configuration drift and others over a period of time. So now that we talked about some of the principles, let's look into the patterns and practices that have worked for my teams and me over the years. It goes without saying that even a script that you run occasionally to fix an issue needs to be put in source control. I have been in places where no one knows where a script that runs in production lives, who created it, and the history of changes. This is a situation you don't want to be in. Make sure the code is accessible to everyone in the company, even for developers that don't make changes to that code base regularly. An exception might be a legal reason, but providing visibility otherwise to everyone in the organization really helps. That helps your consumers understand, even troubleshoot issues, and they might even contribute to your code base if they can see it and they need changes. So it enables better collaboration. Um, but yeah, like I have seen places where different teams, like infrastructure team, has a separate source control system that no one has access to. That is an anti-pattern. Modularizing infrastructure as code, like you would do with your software code, helps with maintenance, readability, as well as ownership. It also helps in keeping the changes small and independently deployable. Refactoring IST is relatively difficult compared to software, especially for critical pieces like DNS records, CDN, network databases, etc. So being biased towards over abstraction front works better, even if that means dealing with slightly more complex ISC than needed. Uh, Also, readability is pretty important. So as you modularize your code, version them, making that readability aspect is very important. And as I mentioned, ownership. So basically, as you modularize your code, you can have your various layers, like networking owned by the networking team if you have one, or security aspects owned by security team. I'm not going to talk about this slide in detail, but here's a typical example of your infrastructure layers. From the bottom, you might have some bootstrapping that you do for your accounts. You might have, account level settings or common storage. Then you might have like networking layer on top. Then you might have some kind of a platform like a Kubernetes cluster or database cluster. And then you have your app. So basically, as you can see, there are various layers of your infrastructure, and there might be various teams that might own those various layers. So having that kind of modularization or breaking things into various layers helps you maintain and have your various teams own those various layers. So there's a misconception that with infrastructure as code, you don't need any documentation. Agreed that it's less documentation as you are codifying all your changes, but you still need documentation for troubleshooting. There might be playbooks or runbooks that you have that allow you to provision something or troubleshoot something, or even onboarding your team members or onboarding your customers. I have seen a few folks also generate documentation from infrastructure as code, which can help sometimes. And I understand documentation is hard. Just like with code, making sure that you have just enough documentation to convey the message you want is important. More documentation doesn't mean it's better. And out of date documentation is even worse. So keeping documentation updated and also making it available when the user needs it is very important. Here's an example. If you display an error message, it's a good idea to include a link to the documentation to troubleshoot issues like that. Also, having runbooks for typical scenarios like troubleshooting during production issues helps your teams. Also, try to keep the documentation closer to the code. What I mean by that is a lot of times you might have various systems that you use for documentation and you use source control for code. If those things are really apart, users have to, or engineers really need to make sure that when they update code, they have to update the documentation in some other system. So using techniques like including a checklist in your pull request template, where you have a checklist where it says, check if documentation needs to be updated, as simple as that would help engineers remember to update documentation. But if you can keep it closer to the code, so let's say within your source control itself, that maybe generates the final documentation, or even just exposes that somehow from the source control, helps engineers remember to update the documentation. Like in software development, you need to think about testing your IAC at various levels. This diagram is my attempt at test pyramid for infrastructure as code. So the idea here is that as you go up the test pyramid, the tests are more costly, they are more brittle, and they take more longer to run. And they also require more maintenance because they are more heavy and they take time to run. So for these reasons, and to get faster feedback, you should run tests at the bottom of the pyramid as often as possible, and the test at the top less frequently. So as you can see at the bottom, the first one is static analysis. So if you're using tools like Terraform, you can use Terraform Validate or TF-Lint. Or if you're using Puppet, you have Puppet Parser Validate. These things are usually available. Like most of the tools have some kind of validation that is quick and easy to run. So you can easily hook it up with your IDE if you use one, or also run locally before you create a pull request. The next one up the chain is unit testing. So unit testing allows you to run things that test a unit of your code. Now, one thing I would like to say about unit testing and infrastructure as code is you might actually not need unit testing for some of the tools. So, for example, if you're using more declarative and more idempotent code base, which is declarative, you define the end state. It's actually tool's job to get you there. So you might not need some unit testing. You might not, you don't usually have if else logic or conditionals in your code. But in case you have a code written in Bash or Chef or something that has some conditionals, in those cases, you can use frameworks like BATS or Chef spec to actually write that unit test. Then if you go up the pyramid, there are integration tests, and there are tools like InSpec or GAUSS, and there are other tools available as well that allow you to run integration. So in this case, you might want to provision your infrastructure, might even provision it as an ephemeral environment, like a temporary environment. You can run these tests to validate that the infrastructure is provisioned the way you want. You can run some security tests as well to make sure your buckets are not public, for example, or you have proper security controls in your database. And then the last but not the least is running smoke tests with a dummy application. So what I mean by that here is, let's say you're provisioning your networking and a platform layer where you're provisioning some Kubernetes cluster. You might actually want to deploy an application to that cluster, just a dummy app that kind of is close to what usually you would be running on that cluster, and then run some kind of a Selenium or JMeter test just to validate that you can hit the API or you can load the UI. This way, you know that you can actually run something, an app on that cluster. Now, this is often overlooked aspect, right? Security and compliance. Do we need to really think about it? I have had a lot of people ask. Yes, of course. So things like identity and access management, right? So in a lot of like, how do you actually provision your infrastructure? But also you need credentials to provision your infrastructure. So using things like role-based access control, rotating your secrets that your infrastructure as code uses is important. Uh, so using things like RBAC will allow you to reduce the surface area of attack instead of giving all the access to the user directly. And then managing those things, right, like key rotation and things like that, is really important. Secrets management, right? So you most probably need secrets for provisioning infrastructure. Your initial secret that allows you to provision the infrastructure, but also there might be other secrets like what's the database password going to be if you're provisioning database. So use some kind of a secret management tool. HashiCorp Vault is a good one. AWS Secret Manager or any cloud provider you use, all of them have secrets management rather than storing it in a plain text somewhere or putting it. Uh, and there are other tools available that allows you to store encrypted values in source control as well. Security scanning. So if you're provisioning an environment, scanning things like Docker images or even scanning your infrastructure as code to see that there are no potential security issues, helps you avoid any security issues in production. And then last but not the least is the compliance, right? So a lot of you might be working with companies that have compliance requirements, but also there are region related compliance, like if you are in healthcare domain, you have something like HIPAA, or you have PII requirements, and all kind of different requirements depending on region as well. So having that kind of incorporated, and also using things like compliance as code that helps you kind of catch those issues early on rather than after deploying to production. So yeah, traditionally people have been using manual checks for some of this for security and compliance aspects, but having these automated and running them early on in your cycle helps you avoid that production issue. So all the steps mentioned earlier should be brought together, and the infrastructure as code should be executed with appropriate checks in a certain sequence to provision infrastructure with confidence in various environments. For this, I'm going to talk about two various options. First one is just an ISE pipeline that demonstrate a typical sequence of steps in a pipeline. I have used various tools like Circle CI, Jenkins, all of like there are so many tools out there now. I don't even remember all of them. This example uses Circle CI, but you can use any of those pipeline tools basically to do this. So this pipeline provides visibility to everyone who is dependent on the infrastructure that gets provisioned. It also notifies appropriate teams when there is a failure. So let's start from the left, right? So you have some kind of a CI, continuous integration, that runs anytime you push code to your main branch, let's say. So you can run some static analysis tests that we talked about. If you have unit tests, you can run those unit tests as well. After that, once that's done, it's a good idea to provision an ephemeral environment. Ephemeral means like a temporary environment that you can spin up, run all your tests, etc., and you can bring it down. So you can spin up this environment, run your ISE, spin something up in your cloud provider, on premises, wherever you're doing it, and then run like compliance tests or integration tests, any security stuff that you have, any other smoke test that we talked about in the test pyramid. And then once all of that looks good, that's when you actually deploy and provision your infrastructure in production. And then you also run some smoke tests after that. So this example is just for like, one of the layers, right? Like provisioning VMs. But of course, you'll have your account level infrastructure as code, your network layer or application layer. All of that would kind of fit in as separate pipelines that actually depend on each other. All right, so the second approach of executing infrastructure as code is by using GitOps, which extends infrastructure as code and adds a workflow. The workflow in this case is usually a pull request process that usually engineers are used to. And then they apply those changes to production or any environment for that matter. It could also have a control loop that verifies periodically that the real state, the desired state, and the real state of infrastructure are same. So if something happens along the way, this control loop can catch, right? Something that is an engineer making a change directly to infrastructure, or some other change affecting your environment. That control loop can catch it and then also enable kind of reconciling that. So GitOps can be used instead of ISE pipeline as defined in the next this slide. So let's look at this quickly from the left. As you can see, you create a pull request. Someone within your org actually reviews. You run your test and stuff, plan and stuff. Then someone within your org or your team actually looks at the PR, approves it. You merge the changes. Once the changes are merged to the main branch, it automatically runs and apply to whatever environment you're deploying to. So the whole process is driven by this pull request mechanism. And then you could also have like a control loop that I mentioned that could keep on checking whether the desired state in the source control is same as the actual state in your environment. And then it can also enable syncing between those. All right, so that's all about infrastructure as code. I actually wanted to give a sneak peek onto something else that's above infrastructure as code and something that we have. We actually use that in one of our products, one of the product that we have called Z Lifecycle. And the concept, what we are calling is environment as code. So Yeah, it's another thing as code, right? So let's actually look at how it works. So it's just an abstraction or infrastructure as code. So as you can see in that box that I say Terraform, and you have individual Terraform for your networking, your platform, Kubernetes cluster, whatever, database, and then let's say you have add-ons. As you can see, it has like a relationship from networking, and then you have your platform KDS that depends on networking, and then your database that depends on networking as well. Uh, Typically, what there are few options of actually achieving something like this, because developers don't need just like a networking layer or just your Kubernetes cluster. They need the whole thing, right? They need the entire environment. How do you get that? There are two ways. One way is you can write like a monolith infrastructure as code that gives you the whole thing, right, in a single run. But that causes a lot of issues, right? Maintenance nightmare. Your state files, if you're using Terraform, becomes large. It becomes slow. So typically, people break that infrastructure as code into separate, components, and then they run and tie all of that together in the pipelines, right, that we looked at. But then that pipeline code becomes messy. That pipeline code is not meant to run and maintain that relationship. You gotta reverse the logic to kind of do teardown and stuff like that. So environment as code in this case kind of manages all that for you. Uh, so essentially, I'm not going to go through the definition. Actually, you know what? Quickly go through it. So environment as code is an abstraction over infrastructure as code that provides a declarative way of defining an entire environment. It has a control plane that manages the state of the environment, including relationship between various resources, detects drift, as well as enables reconciliation. It also supports best practices like loose coupling, idempotency, immutably, etc., for the entire environment. EAC allows teams to deliver entire environments rapidly and reliably at scale. So, if you kind of look at the difference between environment as code and infrastructure as code, I would say infrastructure as code automates your various Lego pieces, so your infrastructure resources, or maybe a group of them, right? So let's say your networking is a group of resources, your platform layer or your database is separate. So you can automate those things with infrastructure as code. What environment as code is, it automates how those various Lego pieces are connected to make up a Lego toy, so your entire environment. So kind of the difference between those. And then here's a more detailed diagram. I'm not going to go through it because I know we are running out of time. But if you're interested in infrastructure as code or even environment as code, I have been giving talks on environment as code, and we have some articles on our website as well. All of that you can find if you go to that link at the bottom. Let me see. This is how you can visualize your environment as well and stuff like that. Okay, yeah, this talk is based on a book I contributed to. But basically, as you can see on the left, go to that bit.ly link, isc-do.
I think we lost you there, Ardosh.
Any questions or anything, please let me know.
Excellent, Ardosh. Very good presentation there. I really like the idea of environments as code. I was taking a lot of notes there. So that seems like a compelling idea that a lot of people are going to want to check out, don't you think?
I think so. I mean, I've heard a lot of, so I've been giving this environment as code talk recently. And then, like I said, we've been using that concept in our product called Z Lifecycle that allows you to kind of automate the environment. So yeah, I mean, I've been hearing various things and thoughts, and like, I think the idea is sticking is what I've like, people are like, yeah, we need the whole thing. We don't need like this one thing, or we don't want to write monolith infrastructure as code because that becomes painful to manage. So yeah, I mean, that's what I've seen, but it's still kind of early on.
Yeah.
And we are building more and more kind of materials, articles, and talks around it. So yeah.
Yeah, it takes a while for something to catch on, though, doesn't it? It's not instantaneous.
Exactly. Yeah. Totally.
And congratulations on the book as well. That's great that you're part of that book. That looks like a really good book that you contributed to.
Yeah, it's just one chapter. I think
Mhm.
a bunch of authors. It's an O'Reilly book, and yeah,
Mhm.
just contributed. Yeah, it's just a fun. I like writing. Well, I got used to writing. I used to hate it, but I think as I did more and more of that, yeah,
Yeah,
it's fun.
excellent. Well, Ardash, we really appreciate your time and joining us. Thank you so much.
Yeah, thanks, Tom, for having me. All right.
Excellent. Cheers, everyone. We'll see you
Yeah.
soon.